Is that working? Okay, I think that's great. Okay, so this will just be a quick run through of ANSYS, pretty much ANSYS Workbench. If you were there for my last workshop, we talked a little bit about what each software ANSYS has available. Workbench being kind of where everything that your project workflow basically is gonna be. So you can see on the left here. So it's really small. Can you see any of these, by the way? Any of these words? Is the
I can barely make out a few. It's kind of like cut off.
okay, because ANSYS doesn't like 4K screens for some reason, so it doesn't show correctly. Everything is super tiny and it doesn't display correctly. But you can kind of make out what each one of these are just by reading the top of it. If you don't have a 4K screen, or if you do have one and you want to turn down the resolution, you'll be able to see these kind of just fine. So let's just choose. So actually, let me just show you the part that I've chosen. Are you familiar with what a thrust plate is for a rocket?
Not really.
So it's at the bottom of the rocket. Basically, it's what holds the motor, and it's what makes sure the motor being pushed up, all that force is transferred into the rocket. So it's kind of what takes the brunt of all the force from the motor. In our case, it's just a solid rocket propellant. So you can kind of imagine this plate sitting at the bottom of the rocket, and poking out the back of this is the nozzle for whatever propellant that we have. And the nozzle sits directly on this ring right here. And it's screwed into the side of the rocket from here. 1, 2, 3, 4, 5, 6. And then you can see this lip right here sits right on the bottom of the rocket. Essentially, this is a metal piece that takes all the force from the motor. Were you here for my last workshop?
Yeah, I was.
Okay, perfect. So just looking at this, what do you think is not necessary to sim? It's a pretty simple piece, so there's really not too many simplifications that we could make, but just judging from this, what do you think we can do?
Probably the 6 bolts I'm seeing might be
Yeah,
unnecessary.
yeah, exactly. So if you look here, these edges, that tiny space, those can get really difficult to mesh. You see here that they don't have threads, which is good. Typically, if a bolt has threads, those are pretty much impossible to mesh. They get really, really difficult. But in this case, we're not too worried about the actual bolts themselves. We just want to see how the force is transferred through this plate. So if you were looking at if these bolts would survive the amount of force that is being generated, then keep them in. But in this case, yeah, it's just unnecessary small details that we can just go ahead and delete. So you can just highlight each one here and delete them just like that. There's actually one other thing that we can do to simplify this. What do you think that is?
Actually, I had a quick question. So I
Yeah.
noticed you just deleted the bolts, but is there a way to like just hide it from like your mesh, like temporarily hide it, just so it's not in the simulation itself, but it's still there?
Oh,
Or do you just Control Z?
I just Control Z, and then I'm pretty sure you can, hold
Oh,
on.
okay.
It's
I see
so
what you do.
this doesn't necessarily get rid of it. It's you can, hold on. If you suppress for physics, I'm pretty sure it doesn't get meshed. I personally haven't tried too much of that, just because it's, I don't know, I don't find it too useful to still have it in your final result. But if you do want it, if you just do suppress for physics, then what that should mean is that it's not included in whatever model you're solving for. But I just like to delete it so I don't have to have any complications in the future. Like, for example, if this didn't work, then I'd have to go all the way back to this step, delete them, and then go all the way back forward, which can be very tedious for more complicated parts. But yeah, you can play around with that. I should try that one day, but I just haven't. So you can kind of see now, this is what the piece looks like. If you want to simplify it one step further, what do you think we would do?
Maybe get rid of the circular base at the bottom.
So the circular base is actually structural. It's kind of, it is needed for this part, because the motor will sit right there, and then this part sits right at the bottom of the frame of the rocket. So it is going to take a lot of force, but what we can do here is something I didn't really go too in depth on, but it's symmetry. So we can actually cut this in half because it's completely reflective. It's symmetric up to itself. You can cut it in half and then say that this, what's happening on this side is the exact same for what's happening on this side. Because it's a circle, it's a triangle kind of piece in the middle. So you can just cut that straight in half and fold it over. I'm not going to do that for this because it makes it kind of tougher to visualize what's happening. And it's just another extra step that's going to take a little bit of time. Plus, I find it easier for, it also just looks better to have this whole thing in your final result. So I'm just going to keep it like that. But you would do that. You would do the symmetry. You'd cut this in half if you didn't have enough nodes, or if you had too many nodes to work with. Like cutting this in half would reduce your mesh size by exactly half, which would make running your simulation 2 times faster, which can make a huge difference in some cases. Like sometimes simulations can take hours, maybe days, and if they're huge simulations, then sometimes even up to a week of just solving. And you want to simplify that as fast as possible. You want to make it as fast as possible so you can see your results, and then maybe even you might have to do it again for some design changes. But yeah, you can just cut it in half and then flip it over. So I think we made all the necessary design changes that we need for this. We basically kept it the same. You see all these edges, they're still there. I mean, you can just kind of keep it as it is. But we move on to the next step. And ANSYS has analysis systems. So this means that it's like your workflow. If you saw my first presentation, you see, I told you guys how you can basically drag and drop this into an area and then work from 1, 2, 3, 4, just go down. Or you can take individual pieces from down here, component systems. So for example, this is a geometry component system. It's the exact same as this block, just individual. So I can just drag and drop this right there and put a completely new geometry in. This is useful for if I want to copy and paste my geometry around. So for example, I tested if this entire geometry would work earlier. So I made it over here, copied and pasted it over here. And then I dragged over my static structural block and just connected them. Because this is the geometry I want to do my analysis on, I just take it, drag it on top of the geometry here, and now they're connected. So now I can run through this whole thing using this geometry. If I had copied and pasted this over here, I can use something completely different. Maybe I want to do some sort of thermal analysis, I can just throw it over here, say that the geometry is the same, and have a completely different setup. But I'm not going to do that for this because we don't have to go too in depth as to how that works. Delete. Okay, perfect. So I don't know if you can read any of these tiny, tiny words, but this first step, engineering data, is describing what materials you're using. This is the very first thing you have to do in order to do any FEA, describing what materials you have. I'm just going to run through this really quickly. I'm not going to go too in depth into how you pick out your materials, but basically ANSYS has a whole list of materials that you can use. I'm going to just choose from the general materials, which has aluminum. And since our team mostly works with aluminum, I'm just going to add this, the plus sign. And now it's right there. So we have the option to choose between aluminum alloy and structural steel. Go back, Geometry already has a check mark. Model has a refresh button, which means that it's not been fully defined yet. Question mark means that you haven't even opened it. So, well, you can have a question mark if you do open it, but question mark just means that these steps first need a step before it to be finished. So this step hasn't been finished yet, so all of these have question marks. Let's open up the model. This is where we'll do our meshing, set our boundary conditions, and run our results. And it takes a while, but you can see down here this little stoplight. If this light says starting something, if there's a red, don't do anything. Don't press any buttons, don't exit out. You will crash the software and potentially your computer. It's happened to me multiple times before. I've had to restart. Basically just let it load for however long it takes. If it does take forever, like I'd say and upwards of 10 minutes, then you may have to restart your computer, just hard reset. But you can see that this just kind of takes a little bit of time, which we are just going to wait for. Ooh. Oh, you can see down here that it's loading from a space claim, which is the CAD software that ANSYS uses. And we have our part. You can maneuver around this just like you would any CAD software, you know, left, right, pan, up, down, pan around, zoom in, out. It's just a regular CAD software on your right. On your left, you go down step by step. Geometry. This is the piece that I just put in. And you can see that there are two pieces. So let's see what the material is. Right now, material assignment to structural steel. We'll be making it out of some type of aluminum. So I'm going to put aluminum. And that's all I need to specify. Don't worry about the rest of these options. So assignment, aluminum, boom. And you can see that you can kind of read off the rest of these. It's not very important for what the rest of what you're doing. You can, you know, open up these, kind of play around with what these settings do. Not too useful for the analysis portion, but kind of, you know, make sure that all of this looks right. Next one is setting up coordinate systems, connections. You can kind of ignore these two. Materials we already set up. You just open it up, you see your aluminum alloy, your structural steel, and it'll give you all the data that you have on that. You can also put in your own materials. For example, if we're working with fiberglass and we want a really rough estimation on fiberglass, ANSYS doesn't have that information, so we have to look it up and put it into ANSYS, and it would appear here if we set that up. Coordinate system, this is just your normal work plane. You can see that it's just sitting in the middle of the part, kinda. You don't have to worry too much about this. You can set up different work systems if you want, global work systems, coordinate systems. We won't worry too much about that. Connections. Now this is actually important. You see these two parts. How are they touching? So we got rid of the screws. Are they just falling off each other? How is ANSYS going to think about the way these two pieces interact? And this is kind of a more simple assembly. There's only two parts to this, but say you're working with an entire rocket. What do you make of the screws? What do you make of each piece that's touching? And that's what the contacts are for. So we can kind of see, assume that these pieces are bonded. What that means is they're one piece, basically. You can see your ANSYS kind of knows that these two are different pieces. This is one piece, this is another piece, and they're touching each other on this surface. You can change this to be frictional, and you can specify some coefficient of friction, rough, frictionless. Frictionless, they're basically just sliding off each other. Bonded is what we would mostly work with. And this kind of makes, this is just an assumption. This is one of the areas where you might have an error. If you assume bonded, oh, shoot, not that one. If you assume bonded, but this really isn't, your results will be very off. Let's move on to the next step. This is the mesh. we talked about how important it is to get a good mesh. ANSYS has an okay randomly generated mesh. So if you just right click, generate mesh, or if you go solve up here, it'll generate a mesh to its best abilities. And you can kind of see that it's okay. What are some kind of criticisms you can make of this mesh as it is, just by looking at this?
I can tell like in the circular base part that it's really bad, like the gaps are really big.
Right, so there's huge meshes here. What about for the smaller geometries? How does it kind of react to that? You can see, basically the first thing I see is each of these holes. You can see that it's very, very kind of not well described. It's like there's a star pattern around them and you want it to be a circular pattern. That's not the best, but you know, these holes, we don't really care what's happening too much around them. So we more care, right, about this bottom area, and these meshes, these cells are massive. One thing you can do to actually tell how good your mesh is if you go here, mesh, display style, element quality. ANSYS will tell you how good your mesh is from a scale of 0 to 1. Blue is good, red is really bad, anywhere in between is not where you'd want to be. You'd want to be in the blue to light blue area, and you can see we're all in the green or yellow, which is not great. And then for the more skewed triangles, we talked a little bit about skewness and other mesh metrics. You can see that those have the red number or red labels. So very bad mesh right now. And we can improve this by right-clicking here, inserting any of these. And it's going to take a while to learn about what each of these do, but I'm just going to go through them really quickly. I'm not going to explain them too much. I can provide resources for learning what each one does, but I'm just going to use kind of what I think are the more important ones. So method kind of determines what shape is going to be used and how it's going to go about doing that. So I select the geometry. You can choose between tetrahedrons. So that's basically just going to be triangles. Hex dominant, just squares. And the rest of them are a lot more complicated. So you can kind of stick between these two before you try to figure out these ones. For now, I'm going to pick this one because I kind of like how it turns out. And I'm not going to explain too much of what each of these are, but I guess if this is a video, you can kind of go in and pick out what exactly it is that I'm doing. Let's generate that. So first thing you'll see is not much has changed. Well, actually, I guess it became a little better, but you can see now that it's more structured around the outside. So these are more squarish squares, and there are more squarish squares around the circles. Now, what happens when we make those smaller? So mesh insert sizing. This is where you determine your sizing for every single node. So you go here, apply element size. Let's do something like 0.01, just as a random number thrown out. Okay, so not much changed. That means that 0.01 was not as small as we could have gone. So why don't we go a little smaller? 0.01. Also be very careful about making this body sizing a lot smaller. You know, 10 times smaller body size does not mean 10 times fewer meshes or fewer cells. Sometimes it can jump up to the 100,000 range if you're not careful. So make your steps pretty small if you're, oh, shoot. Okay, so I may have gone too small. That's why it's taking forever. You can see down here just how long it's taking. And it's done. Okay, so you can see that was way too small. We went just a factor of 10 on the element size, but already you can see how much smaller it's become. Now this multi-zone, you can see how there are so many square cells. And that's kind of what this one does. This one tells it what shape it should be to the best of its ability. This one tells it what size it should be. Now, this is way too small. Let's go back up. Maybe a 6 or 6. Why not? One thing you have to be very careful about with ANSYS student version, which is what I'm using right now, is that there's a limit to the number of nodes that you have. So if you go to mesh and statistics, you can see that right now we're at 11,748. The limit is 32,000. Once you reach 32,000 and above, you will not be allowed to do a solution. They just won't let you. So you have to be very careful about balancing out exactly what size your mesh should be. So I'm just going to play around with this a little bit, just pick out different sizes, and then monitoring exactly how many nodes I have. So this is 15,000, that's good enough. Let's move on. You see it's dark blue pretty much, so you don't really need to go much farther than that. Insert method. I'm going to go through this top part pretty quickly because I don't want to take this to take too long. So I'm going to choose tetrahedrons because this is a more complicated geometry. And because I don't want to take too long, I'm just going to throw in a size. Let's make the 0.008 or something. Let it do its thing. Okay, so it's kind of big. You see all these red lines over here. You can see how skewed these triangles are. Typically not a good thing. We're working at 15,000, so we can bump it up. Let's go to, not too small. 19,000, why don't we go smaller? Don't crash, don't crash. 39,000, okay, we crossed the threshold. We have to go backwards now, but you can see how much better it is. According to this element quality display style, we are now within the blue, light blue, and some yellow area. All right, as soon as we go under the 32,000 mark, I'm just going to go straight into solving. So you can see why 24,000. Ah, shoot, we can go one better. You can see why ANSYS now is pretty useful in terms of making your meshes. If you went into SolidWorks, you would not have this amount of customizability over your mesh. You basically have a custom, or not a custom, an automatically generated mesh, and you just kind of drag a slider and see how, and it basically just gets smaller as you drag it along. With this, you can choose exactly where your mesh gets smaller. For example, this mesh is larger than this mesh, or however way you want to configure it. And you can play around with the exact sizing of everything, as well as the shape of everything. So we're at 29,000, that's good enough. Let's go into our boundary conditions. Static structural, let's say we want to solve, or this is where we put our boundary conditions. Static structural, right click, insert a force. So this is the force of the motor. Up here you can see this selects a face, this selects an edge, this selects a vertex. I want to select an edge because this is where the motor is going to be sitting. So these two edges right here. Let's say 200, well, let's make that actually 750 newtons. Typically a motor will not be that much, but just for the case of this demonstration, I'm going to make it that much. So that's our first boundary condition, that there's a force pushing that way. And now we need a second boundary condition, how everything will end. In this case, we want a, where is it? Fixed support. Where? Ah, there. fixed support. So this means that whatever I apply this to does not move. And because this sits on the bottom of the rocket, that can't move. So I'm going to put that there. So now we have our boundary condition, 250 newtons. And then this is not moving. You can kind of imagine what this is going to look like. This force is going to push upwards and it's going to bend in that direction. Oh, I have to pick a direction, right? So you can just kind of choose any flat area, this line, and flip it, right? Because the motor will be pushing upwards on this part. Solution, let's find the total deformation, the total stress, and let's find our safety factor, which you can find in the stress tool, max equivalent stress, safety factor. So what we do is right click solve and it'll find all of those for us. Just have to wait down here. Are you familiar with what a safety factor is?
No.
So this is basically the number that you have to multiply whatever it is you put on this to break this part. I'll show you what I mean by that. The minimum safety factor is 9.3236. What that means is the whatever stress we have, multiply that by 9.3236, and this part will break. So that is your safety factor. Typically, you want a safety factor of like above 1.5. That's NASA's requirement. But in our case, because we're students and because we have no idea how accurate this is, we want this to have a very nice cushion, like above 5. What this is kind of like, if the force is what force I put is 750, you can kind of estimate that 9 times that will break this aluminum piece. So that's a safety factor. If this safety factor was less than 1, then this piece will break. And you can see the total deformation here. And then you can play around with the visuals. You know, maybe you don't want the mesh, or maybe you want to just the outside frame, or maybe you want all the elements, you know, whatever. ISO lines, smooth contours, contour bands, equivalent stress. And you can go in and poke around a bit. So let's say we see that there's a lot of stress at this corner right here, but how much exactly? So we do label, is that what it was? No, maybe it was probe. I don't remember, but it was one of these things. Yeah. Oh, there, probe. Maximum, minimum. Okay, so our maximum is somewhere in there, our minimum is somewhere in there. So you can kind of see how that works. If you want to figure out the value there, then you go probe, just click there. You can also scale the amount of deformation. So let's say we want it to actually be the amount of deformation that we would see on launch day. We do true scale, and we can see that it really doesn't budge at all. We can also exaggerate it if you want to just be funny, I guess. You can just like poke it, see how much it stretches. This kind of gives you an idea of the way that your part will break, the direction that it's moving towards. But yeah, you'll kind of do this until you have something that you want. I'll basically, if I'm doing an analysis, I'll take the equivalent stress or the total deformation, snap a picture of it, and kind of explain the safety factor and the maximum minimum stresses, why that is, you know, what it's from, what assumptions I'm making, what geometries I got rid of, being the screws and whatnot. And yeah, we'll really never know if this is correct either. It's just kind of an assumption. Yeah, that's kind of it for the FEA portion. Do you have any questions about ANSYS? I know this can look a little overwhelming with the number of options there are, but if you just work at it one step at a time from the left, as you click on it, you have your specifics down here. So mesh specifics. You can open these up, but they're really not too important. You can go through them by yourself if you do choose to download ANSYS. But yeah, any questions on how Workbench works or what each one of these do? You can also, you can go straight into solution information, and then you can find out kind of what it is you get out of this. Solution statistics is pretty useful. Kind of tells you how you can improve your solution. So increasing the number of CPU cores, basically make your computer better is what it's telling me to do. But yeah, any questions?
I think I got a good idea of what's going on.
Cool. So we have a little bit of time. This is kind of everything I wanted to do, but are you interested in seeing CFD as well?
Yes, I am.
Okay. So I have two options for you. We can do CFD of a rocket setup that I made for SL last year, or we can do CFD for a rotating detonation engine that I'm currently working on for some research that I'm doing. So those are kind of two slightly different things, but they'll kind of show you what the setup for FLUENT is. And you can kind of choose how that works, or whichever one you want.
Let's go with the first option, the rocket.
Okay. Let me see if I can get that open. So are you on high altitude or SL?
High altitude.
Okay, so SL, we want to do CFD for the air brakes that we have on the rocket. And then I was designing a study to have different velocities, different actuation angles of the air brakes to figure out drag coefficients. So as I explained earlier, you can kind of drag and drop these components around. And I did that here in order to have multiple setups. Oh, okay, we'll see if this even works. I hope it does, but you'll never really know. Oh, the mesh isn't there. Okay, hold on. I'll try to go through it quickly as I can, but hold on. Did I put it there or is it here? Ah, okay. I can just do this one. If this is correct. So CFD has a pretty similar setup to FEA, but with a lot more steps. And I'm going to go through them pretty quickly because I want to break them down through the workshops later on because they are pretty important. But I guess this will be a nice little teaser for anyone that wants to do CFD in the future. If it'll load. Okay, perfect. So I'm going to show you the geometry, and you can see I broke it down by each step. Yeah, this is perfect. Let's see. Okay, so it's loading down here. Essentially, the thing I needed to solve for as the simulations engineer was determine the turbulence of the air brakes on the fins. Will it break the fins, basically, or will it cause some catastrophic failure of the rocket? If we have something protruding out of the rocket like that, is it going to cause something to happen to the fins? you can see my setup here. So CFD, you don't model your actual CAD, you model the area around it. So what that means is you take your CAD, you create some sort of box around it, and then you cut your CAD out of the box. It's a little complicated to explain now, but I'll get more into depth about that in the future. But you can kind of see here that this is just a cutout. There isn't actually a rocket sitting in here. This is just a cutout of a rocket. And then I cut that in half. And then I basically said that there's symmetry on this side. So I'll break down what each of these are. In CFD, you have to create what are called named selections. So that's basically what each face does so that ANSYS knows what to solve for. For example, this is the symmetry plane. What's on this side is going to be flipped. And exactly everything that's happening here is exactly everything that's happening here. Inlet, this is where the airflow is going into. Far field, this is just kind of extending as far as we can, kind of just ignore what's happening over here, kind of in simple terms. I'll try to explain it better some other time, but you don't have to go too far into the details. Outlet is just where the airflow is coming out from, and rocket body I just define as all the spaces that are of the rocket. You can kind of think of this as a wind tunnel, where this is where the airflow is coming from, this is where it's going out from, this is the glass area of the wind tunnel, and this is whatever you're putting in it. So that's the model setup. Oh wait, shoot. I'll go into bodies of interest. Actually, shoot. Why don't I do that now? So BOIs, or I believe they're called bodies of interest. It's where you can refine your mesh in specific places. So let me open this up. You see that there are 5 parts here, but there's only 1 part showing. It's because I've hidden these pieces. And what they're going to do is help me define my mesh later. So I don't want this whole thing to be the same mesh size. That's just kind of inefficient, because the things that are happening over here, like airflow happening here, is not as significant as the airflow happening here. So I want my mesh around this area to be a lot smaller than my mesh in this area. And I can do that with bodies of influence. So you can see here that I have a body of influence around my fins. I have a body of influence around the pad, the brake pad for the air brakes. And I have one at the bottom part of the rocket. Okay, so that's a quick overview of bodies of influence. You can see that I've named them some sort of body of influence. Okay, so connected that to mesh. I'm going to open up the mesh now. You'll see the effect of the bodies of influence on the mesh. You can see exactly where they would be. But this is just going to take a while to open. So there we go. Okay, so there are the bodies of influence. This is the cutout of the rocket. And you can see that right here, where I put the body of influence for the brake pad, is a lot smaller. And if I do the section plane, wait, maybe I can cut this so we can see it better, but that's not the best cut. There. Okay, so you can see body of influence for the fins. The mesh there is a lot smaller than the mesh there, and that's pretty much the only thing bodies of influence are good for, making sure that you're not wasting all this outside area with a small mesh. And that's kind of the whole setup for the mesh area. You can see body sizing, body of influence. You can select exactly what size the mesh is at that body of influence, and it'll do that for you. So that's a very common practice in CFD, bodies of influence, and it's extremely useful. So I'll be going over the specifics of how to do that later on as we progress through the workshops. Or I guess if nobody comes to the workshops, then I'll just explain it to whoever shows up. But yeah, you can see the name selections carried over. And now we'll go into the CFD setup. So that was Workbench right there. That's where we did our FEA. And now we have one more step, which is FLUENT. And this is where we do our CFD. And I'm going to open up the solution. Typically, you'd open up setup, but because I already have a solution done, I don't want to reset the whole thing. So I'm just going to open up from the solution. Now, FLUENT can look very intimidating first time you open it. And there's a lot of stuff that you have to know about. I'm not going to go through every single option or every single part of the setup, but I'll try to explain what you need to look for. So that's the mesh. You'll notice it looks a little, well, not a little, very different than what it did originally. And that's because I changed it over here. I made polyhedral. That just makes it run way faster because there are way less nodes. I don't know if we scroll up, it'll tell you, but I guess not anymore. Oh, okay, never mind. But FLUENT's limit for elements on the student version, or for nodes on the student version, is 150K. So you just have to stay under 150K nodes and you can run whatever you want. Typically, if I didn't have a limit, I'd make this a lot bigger and I'd make way more bodies of influence so that this area was way more refined. But because I am on a student limit, I just don't have the limits to do that. We'll go through it step by step. So on the left, you can see each step. This is, you'll really just go through these one by one. So general, density based, we don't have, I'll talk about what each of these do later, but don't really worry about that. Models. So turbulence modeling is a very, very complicated subject within CFD. There's a lot of reasons why you choose one equation over the other, but you can see, oh, shoot. Viscous, so this is where you define turbulence modeling. And you can see that there are a ton of options. And each one of these is going to have a very, well, maybe not very, but some difference in result. And you have to know why whatever you're picking is the correct one for your case and why it'll be suitable for whatever it is you're doing. Are you familiar with Navier-Stokes equation at all?
I've heard of it once, but no then.
Okay, don't worry about it too much. Basically, it describes how fluid motion works, but it's way too complicated to solve. So they simplify it, starting from no turbulence to a little bit, a little bit, a little bit, a little bit more, a lot more, and then directly solving Navier-Stokes, which you need a supercomputer to do basically. So don't worry about these, just kind of stick from here and above. So that's turbulence modeling. You also have to know how fast you're going. You know, are we reaching near Mach 1? In which case we enter what's called compressible flow. And you need energy for that because at that point, high pressures, lots of heat, you need an energy equation on. I won't go too far into the specifics of that, but you can see a lot of these are turned off because we just don't need it for our rockets. And materials, you have to specify air as whatever it is you're using. You have to specify it as an ideal gas so that we have compressibility in it. I know that sounds kind of counterintuitive, but yeah, you have to specify viscosity and whatnot so that we have the correct effects. Boundary conditions. This is one of the more important ones. So you can pretty much glance over materials and cell zone conditions, go straight into boundary conditions. Far field, I consider it as a wall, basically. That's the best simplification that I can do. If this whole area is a wall, treat this as a velocity inlet because I know how fast our rocket is going. So I can treat this as air flowing that fast. Interior, that's just all this area. You don't have to do anything to that. Outlet, pressure outlet. I'll explain why these are important later, but essentially, you should have an idea of what every single boundary condition does and what it's good for. That obviously that doesn't come from just like straight memorization. That comes from practicing them and figuring out kind of what's useful for you. It also depends on what you know, because in terms of rockets, only thing we know is how fast we're going. So velocity inlet makes sense. But in some cases, maybe pressure inlet is better, or maybe a mass flow inlet is better because we know our mass flow rate, but I'll describe how those are useful later. Symmetry, this wall is symmetric with itself. So it's just gonna flip itself. And that's all you need to know for that. You don't have to worry about anything down here. Methods, I'm not gonna explain what each of these do, but there is a little bit of stuff you have to configure here later on. It's not too specific. Oh, if you want to calculate drag, you need to specify these the parts of the drag equation. So drag is the drag equation is a function of area of whatever it is that you're solving for. So you actually have to put in the area of the rocket, the cross-sectional area of the rocket. Oh, shoot. But we really don't need to worry about that right now. I already calculated that, so I just wrote it in. And then you can calculate your drag, but I'll go to initialization. You have to tell it that all of these cells start at some value. And that's what these do, hybrid, standard, doesn't matter which one you choose in this case. There is a difference, but you don't really need to know why that's the case. You just do this, initialize, sets all of these to 0, run calculation. You set your number of iterations and you calculate. So we'll talk about why iterations, your number of iterations are important, but your solution is gonna have a lot of ups and downs, I guess is the best way I can say it. It won't have a direct solution. It's gonna guess. It's gonna check if what its answer has got is very different from the guess. It's gonna take the difference and then it's gonna guess, or it's gonna try to guess better the next time. And it's gonna keep doing that until the guess and the answer are not very different, until they flatline. That's why the number of iterations is important, because this is literally the number of times it's solving over and over and over and over again. And you can imagine for bigger things, you're going to need way more of these. You're going to need upwards of thousands, and you're also going to have way more cells. So that'll just take ages. So once you do initialization, calculate, it'll run through the whole thing. It'll say finished, and then you do your post-processing. Don't save changes and exit. Post-processing is just where you view your results, because Fluent is not the best. It's not user-friendly. You can't really see everything that you want in Fluent, so you have to go into some other thing. CFD post is what ANSYS uses. And this is where you can view your results. Also, you'll never know if these results are correct. They could just be, I did this sim relatively quickly, so they're definitely not correct, but you can see how I set up my post-processing visuals, how I put some planes down, put some contours, some cool contours, and evaluated the turbulence of the air brake on the fins. And you can see here, the result that I got was that the fins, that the air brakes don't cause significant turbulence on the fins. Just play around with what each of these do. Yep. You can see that this is a velocity contour. You can change it to be pressure contour. So you can see this is an area of high pressure. You can change it to be a temperature contour. So you can see that temperature increases right there due to us going so fast. And yeah. So this is a very, very quick run through of FLUENT. It also isn't from the beginning. I kind of skipped over some sections. Do you have any questions about how everything works, or about how FLUENT, the solver, works, or how I can get some different results? Or
No, I think I get it.
cool. Yeah, and then you can see how there's no flow next to the wall, which you can expect because it's a no slip wall. And yeah, if you do choose to download ANSYS, then yeah, you can play around with kind of how you do FEA. I'd recommend doing FEA first and then moving to CFD, because CFD has so many different ways of doing it that it can be overwhelming. But there's a ton of YouTube videos out there, so if you ever find anything, that'll be pretty good to know. Just follow a YouTube tutorial because they have tons of those. But yeah, that's everything. Don't save. I'm gonna stop the recording.